Hello and welcome. In this lecture we're going to be talking about Y and delta conversions, and this is another fundamental topic in the field of electrical engineering. The applications of this topic can be found in power engineering and radio frequency engineering, to be specific. In power engineering, when you get into three-phase circuits, these concepts become handy, and in radio frequency or RF engineering, when we get to impedance matching and T and pi networks, or Y and delta networks, which are interchangeably used as seen in the parentheses, we'll see why these become useful. But before any of that, we'll see why it is useful for our application in this course, which is about the fundamentals of circuit analysis. So without further ado, let's go ahead and jump into the contents. So the first item is irregular resistive networks. And what I mean by irregular is not it is not a official nomenclature in any textbook. What I mean by irregular is any network where the constituent resistive elements are not necessarily in series or parallel in a very simple manner, as we've seen before. An irregular case would be one where they're not easily you can't easily combine them to an equivalent resistance in terms of series and parallel constituents. Then we're going to talk about Y networks or T networks, and we'll see why these are interchangeably named. We'll see that very soon. Then we're going to talk about delta networks or pi networks. We're going to then see how to convert delta networks to Y networks and vice versa. We're going to see a proof of that. Then we're going to see a balanced delta and Y network, an example of each. Then we'll see some more examples with numbers and, of course, a quiz. Before we jump into the first topic, let's briefly give credit to author E. Kennelly, which was an important electrical engineer that contributed to this field with a variety of findings. One of which is what he worked on with Y and delta networks, but other contributions are to the concept of impedance and using the idea of phasors, along with a guy named Steinmetz. Again, we'll see these things as we go forward, but that's something else that he worked on. And lastly, something else to mention is the Heaviside Kennelly layer of the atmosphere, otherwise called the E region layer or E region. So that's just some buzzwords to tell you and demonstrate his contributions to this field. So let's go ahead and talk about the first concept, which is the concept of irregular resistive networks. Again, I'm just calling them irregular. You may not find this in textbooks. So what I mean by that is that when you look into this network, for example, you'll see that, okay, I have a R1 in series with some other equivalent resistance. But when I look at these nodes, I see that I have some resistors here, but then I have an R4 which sits in between them. And that makes our job a little bit more difficult in terms of finding the equivalent resistance. I'd like you to go ahead and try and combine this using the old techniques we learned in the previous lecture in terms of series and parallel combinations. And what you're going to find is that it's not easily doable, and therefore we're going to develop a new method shown in this lecture, which is to develop two new three-terminal resistive networks to be used as building blocks of more complex resistive networks. And we're going to see what that means in shortly. So let's go ahead and talk about Y or T networks. First of all, why do we call them Y or T networks? Well, if you look at this building block of a four-terminal or three-terminal really resistive network, you'll see that it looks sort of like a Y, and therefore that's why we call them Y networks. But also, if you simplify the circuit by moving these resistors down to be parallel with this line, this terminals 2 and 4, you'll see that it looks like a T. You'll see the resistors aligned to be a T, and therefore we call them Y or T networks. In RF, you might hear T networks more often than Y networks. In power, you might also hear star networks. So let's go ahead and answer this question. We're seeing a new building block, and we want to just study it a little bit, apply some techniques we've learned, and find out what it's all about. So let's just go ahead and look at the different combinations of terminals and find its resistance. So you might notice that we have 4 terminals, and I have only 12 combinations and not 16. Well, the reason for that is that for every node there is a combination with itself, which I've excluded because it's trivial. The resistance between a terminal to itself is 0 because it's a short line. So let's go ahead and look at the non-trivial cases, which still we're going to see that some of them are still trivial, but these are not immediately trivial, but we're going to prove that some of them are. So we've eliminated the 4 trivial cases, and let's go ahead and find the answer to these questions. Let's find the resistance between terminals 1 and 2. So let's look at 1 and 2 here. How do I find resistance? I apply some voltage. Across those particular terminals. It doesn't really matter what orientation it is, so long as the elements are purely passive or resistive. So I'm going to go ahead and apply this V test. It could be anything. It could be 1 volt, 10 volts, according to the ratings of the resistors. We have to calculate that at some point to make sure we don't blow anything up. So we'll apply this and we'll get some I test. Now let's trace this through. What's going to happen? This voltage is applied here. I have a high to low potential developed across these terminals. This current is going to be flowing through some portion of the circuit. But if we look through, we'll see that as it flows through, it's going to take this path. It should be immediately apparent to you why that's the case, but I'll just go ahead and tell you because it cannot go through this path because this path does not close around itself. It's not a network, it's a open circuit, and therefore there's going to be no current through it, and therefore there's going to be no voltage drop across that resistor. Remember, if there's no current through a resistor, there's going to be no voltage drop across it. So whatever voltage exists at this node is going to be read at terminals 3. If we use a high impedance or high resistance load or a measurement device, which usually is a high resistance, it has a high resistance output, so that it doesn't draw much of a current and interfere with the measurement. So given that, we can see that there's 2 resistors in series, and therefore for the first part A, R equivalent is going to be R1 plus R2. Very simple. Let me decrease the size here. Alright, so that's R1 plus R2. So now let's look at section B. Let me see if I can clear these out. Alright, so now let's say we want to find the resistance between terminals 1 and 3. So let's go ahead and apply a voltage source. Again, it doesn't matter which orientation as long as they're resistors. For example, if there were diodes, that would not be this. That would not hold true. I could do it either this way or the other, the opposite polarity. I'm going to connect these guys up, and again, some current's going to flow. If we trace it through, we'll see that it cannot flow through R3 because again, this does not close a path. There's not a closed path for the current to flow through. That is one of the rules in electronics that you need to remember, is that there needs to be a closed path for a DC current at the very least to flow through. With antennas and things of that nature, we're going to see later on in different courses, or you might see it by yourself in different courses. There can be such a thing, but for now, for circuit analysis, as long as the loop is not closed, there is no current flow, and if there's no current flow, there's no voltage drop across that particular resistor that's sort of open at one end. So here, there's going to be no current flow through R3, and therefore the current's going to go down R1 and R2. And again, we're going to see that the resistance would be R1 plus R2. And in the previous case, I messed up. That should have been R1 and R3. I just noticed that. So in the previous case, for 1 to 2, that should have been R1 and R3. In this case, it's R1 and R2. Let's go to the third case here, which is R1 through R4. So in this case, if you are to apply a voltage source here, you would see that, let's see, plus and minus, and we're going to apply it from this end to this end. So now let's think here. So the current, this is V test, this is I test flowing through here, conventional current. It's going to go through, and as it goes through, it's going to go through R1 for sure. But you can see that it can't go through R2 for the same reason as before. It's an open end here, and it's going to have to flow through R3, and of course it's not going to go through the terminal 2. And I should also mention that terminal 2 and 4 are really the same because they're short lines, and because that's the same node and there's the same potential across that node, it's really the same node. But we're only doing this to make it kind of give us foreshadowing for two-port networks and so on way down the line in these lecture series. Anyway, so the current's going to flow through here. It's going to go through R1 and it's going to go through R3, and therefore the resistance here is R1 plus R3. Okay, so I've gone ahead and finished the rest of this because it's following the same logic as the first few examples. You might notice that a lot of the answers are redundant, and that's because this network is symmetric in some ways. For example, 1 to 2 or 2 to 1 are the same, 3 to 4 and 4 to 3 are the same, 1 to 4, 4 and 1 are the same, and so on and so forth. And do again note that 2 and 4 and 4 and 2, the resistance between them is 0, and therefore I've noted that in part F. Okay, so we've finished that specific topic. Let's just circle the ones that are important though, the resistances that are going to come into play as we go ahead and derive useful results. So I'm going to say R1 and 2y, which would be between 1 and 2, so part A, which is going to equal R1 plus R3. Let's go ahead and record that, as well as R1 3, which is equal to R1 plus R2, and let's see here, R3 and 4, which looks like we're going to derive at some point later. So for now, let's go ahead and box these. Alright, so now let's talk about delta networks or pi networks. So the reason we call them delta networks is that as you can see here, the way this is connected, it looks like a delta, like a Greek symbol delta, although it's backwards, but it nevertheless looks like a delta. And why we can call it pi is because as you can see in the bottom picture, if we move these resistors RB and RA so that they're parallel with, or they're perpendicular to these two lines, these two wires, they look like a pi network. It looks like a pi, the letter. So now let's go ahead and find the same thing as we did before. I'll show you for the first few, but I'll go ahead and do it quickly for the rest. So from 1 to 2 is the following. So what I'm going to do, I'm going to apply it here so it's easier to see because it's a simplified schematic. So let's quickly go ahead and draw this voltage source, and I'm going to apply that here, a VT, some current's going to flow, IT. Now this current, we got to trace it. Where's it going to go? It's going to go through this node, it's going to go to this node, and then it's going to have to, it can go through RB and RC and RA. So it's going to go flow through here and go and go and go and come through, because we have two different loops, right? So we could have this loop through RB, or we could have through RC, RA, and then back to the voltage source, or one bigger loop which is through RC, RA, and back to the voltage source. So for that reason, it's going to be able to go through both, and therefore what we could say is that RB is in parallel with the series combination of RC and RA. Why the series combination? Because since terminals 3 and 4 are open, no current is going to flow through there, and therefore we can just ignore them, and you can just imagine that they don't exist. You can just cross those out, and this looks like if you look into here, we're going to see that it's going to be a RB in parallel with the combination of RA and RC. So for the first one, we're going to have RB in parallel with RA. Oops, messed it up. RA plus RC. For the second one, 1 to 3. Let's see here. Let me clear this up and look at 1 to 3. So if it's going 1 to 3, I'm going to draw it sort of in this manner with the following polarity, and I'm going to connect that here and here, and some current is going to flow IT again, that is VT. And now where is it going to go? So what it can do is it can you can imagine that the current's going to come here and find a couple different paths. So you can go through RC, and it can also go through RB and then back through RA. Again, you can ignore 2 and 4 because they're opens. So what this really looks like is that it's going to be an RB and RA in series, because the current can only go this way, and also the current can go this way, and therefore RA and RB, their combination is in parallel with RC. So what I'm going to say is that for case B, I'm going to have a RC in parallel with RA plus RB. Alright, so I've gone ahead and completed the rest of these. I encourage you to go ahead and check it yourself. Wherever you get stuck, just rearrange the circuit to the simplest possible shape that you can see, and clearly see what the resistor combinations are to give you the equivalent resistance looking through your particular terminals of interest. So let's go ahead and box the important results from this that we're going to use soon. So let's go ahead and write R12 of a delta is going to equal RB in parallel with RA plus RC. Saying 1 to 2, RB parallel R, right. So that's where we're going to have, and we're going to save that. Then we're going to go ahead and save the result R13 of a delta network, which is going to be, let's see, R1 to 3 is a B. That's going to be RC in parallel with RA plus RB. Does that make sense visually? That's 1 to 3. That is going to be the parallel of RC and RA plus RB. And lastly, R34 of a delta is going to be, let's see, 3 to 4 is going to be RA in parallel with the combination of B and C. Let's double check that. 3 and 4 we derived is I, and I is RA in parallel with RB plus RC. Let me go ahead and box this also. Now, one thing that I didn't mention in the previous case that I should have was that R34 is going to be R2 plus R3. So looking from 3 to 4, we're going to see a R2 plus R3 because the current flows through this loop. And given these results, we're now ready to go to the next topic, which is delta to Y conversions. Alright, so now let's begin deriving useful relationships between delta and Y circuits or networks by first converting a delta or a pi network to a Y or T network. So in other words, we want to go from here to here. The orientation is kind of awkward, but we're going from right to left here, delta to Y. So to do that, we have to think about something. So the goal here is, remember, in the field of electrical engineering, what we most care about is when we're talking about blocks or modules or equivalent circuits, is how that circuit or model behaves at its terminals. So the key here is that if you want to convert this particular circuit, the delta, to a Y network, we need the IV characteristics or the equivalent resistance looking through any given terminal to be the same for both. And to do that, and really we got to think about this. So if we're converting the delta to a Y, then what it's going to do is it's going to relate these variables RA, RC, and RB to R1, R2, and R3 in some manner. It's going to relate them in such a way that if I wanted to have, suppose I was given a delta network and I just, for some reason, it was convenient to work with a delta or a star network, I'd be able to just quickly convert the delta to the Y by just plugging in some values to a certain relationship that we're going to derive soon. So let's go ahead and find R1. That's the first thing we're going to find. So we're going to find, we're going to convert to a Y network, so we want to find what R1 is going to be in terms of RA, RB, and RC. So to do that, let's go ahead and start with let's see here. Let's go ahead and find R12 minus R34. So why am I choosing this? So if you look at R12, you see a R1 and a R3. If you look at R34, you see a R2 and a R3. If I subtract this quantity from this quantity, what I'm going to end up with, if I distribute the minus, I'm going to end up canceling a R3 out. In other words, what that's given me is that, let me just go ahead and plug all of those in. So it's going to be R1 plus R3 and a R2 plus R3. I'm just going to derive everything to make it easier to see. So that's my R12 and that's my R34. That's going to equal R1 plus R3 minus R2 minus R3. And of course you see that R3's cancel, but for completeness sake we're gonna go ahead and go through all of these. So that's gonna give me a R1 minus R2. R1 minus R2. And I do recall though that we have to set these equal to each other because we want the terminals to behave the same from one terminal to the other. They should have the same equivalent resistance. So therefore we're going to say R1 minus R2 is going to equal whatever is on the delta side. So R1 minus R2 is going to be, again, R12 minus R34. So that's going to be R12 minus R34. That's going to be a RB. Let me just go ahead and combine them in parallel, which is RA plus RC all over RA plus RB plus RC. And that's going to be, so that what this is this is R R12 on the delta side. We're going to subtract what from it? We're going to subtract 3/4 from it, which is going to be RA times RB plus RC. I'm simply combining these in parallel instead of having a parallel symbol. I'm going to just go ahead and do the actual parallel combination. RB plus RC. If you don't recall this, you should go back to the previous lecture and review it so that it would make sense what's going on. Now let's go ahead and get the common denominator and look at what happens up top. So up top I'm going to have RA, RB plus RA, RB, RC. That's the first term on the left here, the first entire term there. That's going to be minus a, let's see, RARB, RARB, another minus RARC. It's going to be difficult to write this here, so that's going to be, let me move this over, RARC, RC. So let's see how we can cancel, how we can simplify this. So RARB is going to cancel here, and let's see, RARC. Can I do anything there? Alright, so what we're going to do here is that we're going to say R1, R2, subtract that, and set that equal to, I'm going to go ahead and factor a RC out. So I'm going to have RC, and then I'm going to have a RB minus RA. If I'm not mistaken, yes, RB minus RA. And that's all going to be over RA plus RB plus RC. So that is one useful relationship here that I'm going to keep. Now the other ones are as listed above. I'm just going to go ahead and set them equal to each other. R1 and R2, we said that has to equal this R1 and R2, so that's going to be R1 plus R3. I'm just going to go ahead and list these out so it's easier to see as we move forward. So R1 plus R3 should equal the delta version, which is RB in parallel with RA and RC. I'm just going to combine them again in parallel. RB plus RC. Let's go ahead and find the other relationship, which is going to be up here, and that is R1 plus R2 is equal to RC. So R1 plus R2 is going to equal, let's see, RC in parallel with RA and RB. I know it might look confusing, all these variables all over the place, so that's why it's useful to just write everything down and keep a nice record of everything to keep them straight as we go ahead and get into more complex calculations. And number 4, we're going to set R2 plus R3. We're going to set that equal to RA in parallel with RB and RC. And we will see what exactly we'll need to derive what we need. If something is redundant, we'll simply not use it. So let me get another box around these quantities and move forward. Alright, so now we're going to go ahead and our goal was to find R1 by itself. So what we're going to do now is add equations 1 and 3. So I'm going to add equations 1 and 3. You might be able to see why that is. So if I add 1 and 3, I'm going to cancel a R2 and I'm going to get 2R. So if I do that, I won't write that math out. I end up simply with 2R, R1. Again, I'm just adding these two equations together, so you can see minus R2 and R2 cancel, and I get R1 plus R1, which is 2R. 1, very simple. I'm going to add, so then I'm going to add this other equation together. I'm just going to go ahead and take a common denominator now because they have RA plus RB plus RC. So I won't need to write that out. I'll just go ahead and take it out now, or take a common denominator now. Then I'm going to have a RCRB minus RARC. So RCRB, I'm going to just write all the terms here first. RARC, and then I'm going to subtract. I have a RARC here as well. Let's just write these out with the same color. RBRC. Now let's go ahead and look at where's the minuses and where are the pluses. So I have a minus here, which is between the RCRB and the RARC. RARC on the bottom here. Then we're going to have, let's see, did I get that right? And then I have pluses all around when I get to these sections. Right. So now RARCs are going to cancel, and what we're going to have at the end there is RBRC plus RBRC. So that's going to be a 2 RBRC over RA plus RB plus RC. Now you can see that I can go ahead and cancel the 2's out, and what I end up with is that R1 is equal to RBRC all over RA plus RB plus RC. Let's go ahead and box this relationship. So we found the star or Y equivalent of R1 in terms of RA, RB, and RC. And that was our goal, as I stated before. Alright, now I've gone ahead and summarized the remaining resistors R2 and R3 in terms of the resistors of the delta network. If you wanted to do this mathematically, you could use the equations that I showed here above, and you would just have to rearrange them in such a way that you would eliminate other variables and get the particular resistor that you want to find relationships for. But we can also do it a simpler way. Since we found the answer for 1, what we could do is just come up with a rule, a general rule that we could follow without having to do this every time. It's an abstraction. So what we can do is we can start with a delta network shown on the outer layer here with the yellow resistors, and we could superimpose a star or Y or T network into it in the manner shown. And what we would say is that R1, whichever resistor you're looking at, so for example R1 is going to be the multiplication of the adjacent delta networks resistors, so RB and RC in this case, over the sum of the delta networks resistors. That's going to be the rule that we're going to follow. Let me just write resistors here. Resistors. So what I mean is, okay, so for R1, without having to go through all those derivations, we'd say, okay, R1 is going to be the product of the adjacent resistors in the delta network. We have to make sure we understand it's delta network, because we're going from a delta to a star. So we're going to look at the original one and find the resistors that are adjacent to the desired resistor that we want to find, and divide that by the sum. So for example, if you cover the answers here and look at what R2 is going to be, we would have to predict that R2 is going to be the product of the adjacent terms in the previous circuit, or the delta circuit. So RA and RC, which are adjacent, and I'm going to sum that up with the I'm going to divide that by the sum of the resistors, and let's double check here. RA, RC, that's correct. And lastly, for R3, you'll see that RA and RB are on the top, multiplied, divided by the sum. So that concludes this section about delta. This would be a proof for delta to Y conversion. Next, we're going to look at Y to delta conversions. Alright, so now we're going to go ahead and convert a Y network to a delta network. Again, keeping in mind that our goal is to maintain the same resistance looking through each given pair of terminals. And with that being kept in mind, and also remembering what we just found out for the Y to delta or delta to Y summary, the relationships we found, let's go ahead and do the following. And this one you might need a little bit of faith for this, because otherwise we'll have to play around with equations and find it out the hard way. But if we just go ahead and do the following, if you go ahead and take every combination of products for any pair of R1, R2, and R3, let's see what we get. What I mean by that is, if you say R1 and R2, R1 multiplied by R2 added to R1 multiplied by R3, and so on and so forth. So if you go ahead and sum up all the all the possible combinations of products here, we're going to have R1, R2 plus R1, R3 plus R2, R3. These are the possible combinations for multiplication. Now let's go ahead and plug those in. So we know that whatever the multiplication is, it's going to be it's going to have the same denominator. So I'm just going to go ahead and write the denominator down here and square it, because it's going to be R1 and R2. For example, it's going to square the denominator. So I'm going to say RA plus RB plus RC. Let's go ahead and square that. And on the numerator, we're going to see that we have R1, which is RBRC, times R2, which is RARC. So we have RC squared there. RC squared times RARB. Then we're going to go ahead and go to the next terms, R1 and R3, which is going to give us, let's see, let's add that. It's going to give us RBRC times RARB. So now it's going to be RB squared. RB squared times RCRA. RCRA. And finally, we're going to add to that R2, R3, which is going to be RARC times RARB, so RA squared now. RA squared times RBRC, RBRC, BRC. So what we actually should do now is go ahead and factor out a RA, RB, RC from every single term. So let me go ahead and copy this and start down here. So let's get this term, copy it, paste it, and bring it here. And let's say that is equal to, so what I'm going to have that same RARB, that denominator, I'm going to have the same one. Let's see why am I not able to select this. Alright, so get this guy, copy it, paste it, and delete the residuals. Alright, so I have that portion. Now I'm going to say, let's factor out RARBRC, BRC. Let's see what remains. So if I take a RARBRC out, I'm going to have a RC here added to a when I factor out RARBRC, I have an RB remaining, and similarly I'm going to have RA remaining. So what I'm going to have on the top is going to be a RARB plus RC. RARBRC. If you don't see it immediately, I encourage you to go ahead and just try it and write it down on paper to see that indeed you get that. Now what I'm going to do is go ahead and cancel out this term by and take away one of the exponents here, you might notice something here. We defined R1 to be RBRC over the sum of all the delta networks resistors. If you look here now, you'll notice that if I take any pair of these resistors and divide it by or have it, for example, if I take RA and RB and I just pay attention to this pair, what that tells me is RARB over the sum is going to be R3. So I'll be able to find R3, and that's going to be R3 times RC. So in this case though, let's go ahead and find R1, which is RBRC. So I'm going to circle RBRC over that sum, and that's going to be my R1. So now what I did there is I found what RA is going to be. So let me just go ahead and write that again really quickly. So what I'm saying is, let me just say equals RA. Let's just clear the clutter and be able to see it better. Divided by RA RBRC. Now what I'm saying is that since this is equal to this quantity here, if I want to find R1 or RA, if that is my goal, I'll go ahead and isolate RA and get the remaining terms, and I find that that's going to be R1. And I'm going to divide both sides by that. So this whole thing here would be R1. So I'm going to divide both sides by R1. So I'm going to say 1 over R1 on this side and 1 over R1 on this side. And what I end up getting is that it's not looking good. Let me redo this part. What I would get is that RA is going to equal R1 R2 plus R1 R3 plus R2 R3 all divided by R1. Let's go ahead and box this result. Alright, so in this case I've also gone ahead and found out the relations for RB and RC as before to save time, and also to just avoid doing extra math and just go ahead and learn a new abstraction and be able to use this rule from now on to simplify our lives when it comes to doing Y delta conversions. So in this case I'm going from a Y to a delta, as I said, and I'm going to superimpose a delta network on top of my or around my Y network, and I'm going to say, okay, this rule appears as though what it does is it takes all of the possible combinations, all the possible multiple combinations of the Y network's resistors, and it divides it by the opposite resistor. So what I mean by that is, suppose I want to find RA. So what I do is I take all the individual the sum of products of every pair, every possible pair. So R1 times R2, R1 times R3, and R2 times R3, and then I divide that by whatever is opposite to RA. In this case, R1. And what's going to be opposite is going to be in the starting circuit. So it's going to be from the Y network, not the delta network. A way to remember that is, well, I don't know what RB and RC are, so it's not going to be those. It's going to be whatever is opposite to my resistor of interest in the delta network, but it's going to be inside the Y network. Now if I want to find, now go ahead and stop the video and just try to practice this for determining RC and RB, and once you get comfortable with it, you can move forward. So I'm assuming that you've tried it, and you would see that if I want to find RC, I would take all the possible sum of products again for each pair of resistors, and I would divide that by R3 for that's for RC. And you can see that's the case here. I think I mislabeled something here. What I should have said is that this is R3. So and let me check my notes really quickly, and that is correct. So that is what that's going to be. And for RB, then I'm going to take all the possible combinations again and divide by the opposite, which is R2, and that's what I see over here. So this concludes our proofs, and now we're going to go ahead and talk about balanced Y and delta networks. Okay, so now let's talk about balanced Y and delta networks. When we're talking about balance, we're just talking about having the same resistor values for each given network. So in this case, for Y networks, we would say if they all have the same, if they have the same resistors labeled as RY, then that would be a balanced Y network. And for a delta network, if they have the same resistor all over, they would be a balanced delta network. Now let's go ahead and find the relationship between the two if they're the same resistances. So let's say I want to convert from a delta network to a Y network. What I would do is I would just go ahead and plug in for any, because they're the same, I could just plug it for any given relationship that we found before. As you can see up there, let's just say R1. I'm going to just go ahead and find R1. Let's just say this is R1 for now. It doesn't really matter. I'll go ahead and just pick any two of these guys and say R delta multiplied by itself, which would be R delta squared, and that's because any given pair, if you multiply, it's going to be R delta squared, over the sum of all three, which is going to be 3R delta. And what that's going to do is it's going to cancel the exponent and one of these terms, and I'm going to have a R delta over 3. Now if you just solve for this, so let me just go ahead and write this here. Ry is equal to R delta over 3. We're going to box that, and we're not going to worry too much about what this means in the meantime. This is important for power circuits and three-phase circuits. Now we could also go the other way around and say what is going to be R delta if I want to convert from the Y network to the delta network. And I'm going to take all the possible combinations. So it's going to be RY times RY multiplied 3 times. So I'm going to have, added, the products are going to be added 3 times. So I'm going to have a 3 RY squared over just one of the RYs. As you recall, I would divide by one of the RYs, and I would cancel out the exponent of one of those, and what you would end up getting is, of course, the same thing we just found out up here, and that's just another way to show it. So this concludes the discussion about balanced Y and delta networks. Let's go ahead and move on to some examples. Alright, let's go ahead and do our first problem. So in this problem, we're asked to convert the following delta network to an equivalent Y network. So we know right off the bat what sort of equations we're going to need to use. Now I have sort of scrambled the namings of RA, RB, and RC because it shouldn't really matter where they are. What really matters is relative to our Y networks resistors, how we orient these resistors. So what I mean by that is, let me superimpose a, let me make a more visible color. Let's superimpose the Y network onto our delta network, and we're gonna go from there. So let's connect these up, and now what we're gonna do then is whatever these, and it doesn't really matter how I label this. I could have labeled this R1, R2, and R3. It really doesn't matter. so long as we do the relationships correctly, so long as we do the math correctly. So let's go ahead and write it for R3. So we know that for R, let's start with R1 actually. So for R1, how would you go about this? We said that it's going to be the product of the adjacent resistors in the delta network over the sum of all in each individual delta network's resistor. So before we do any of that, let's go ahead and just find the sum of all resistors. So let me say R, let's just say this, let's say sum of R delta is equal to 10 plus 20 plus 20 plus 30 ohms, which is going to give us 60 ohms. So that's what that is, and that's going to help us here because we won't have to keep writing that. So now what I'm going to say is that R1 then is going to be the product of the adjacent resistors in the delta network. Let's make sure we pay attention to which network we're talking about. So we're going from delta to star, so we need to get the original network, so the delta network's sum as well as the product of the adjacent resistors. The product is going to be what? It's going to be RA times RB, which is 10 times 20, which is going to be 200. And that's going to be over 60, so 200 over 60. That cancels, and you get, if that was a 10, that was a 3. You get about 3.3 ohms. That's roughly what that's going to be. Now R2 then, we follow the same procedure. There's no magic involved. We just go through the same thing and apply procedural steps. Now for R2 then, we're going to have the product RB times RC, which is 20 times 30. 20 times 30. That's going to be over the sum, which is 60, as we said. That's going to cancel with that. That 3 is going to cancel with this guy and give me a 2. And that's going to give me a 10 overall. So that's 10 ohms. And lastly, my R3 is going to be the product of RA and RC, which is RA and RC is 10 times 30, which is 300. 30 over 60, and that cancels that. That gives me a 2 while canceling this, and that gives me a 5 ohm resistance. So at the end, what everything's going to look like is the following. So I'm going to have my Y network. I'm going to hack away at it, and connect these guys. And what matters is that I get them correct relative to each other. So if I said that's R1 on the bottom, I'm going to say R1 is a 3.3. And if I said R2 was this guy, that means it's going to be 10 ohms here and 5 ohms here. Now, what this is saying is that looking at the same terminals, let's call this 1, 2, and 3. This is telling me that at the same at terminals 1, 2, and 3, these are equivalent. This is what it's telling me. We have to make sure we understand. We're in the terminal business. We look at terminals. As electrical engineers, we care about across various terminals, how do our modules and blocks work? Are they equivalent? If they are, then we can go ahead and say that we did the problem correctly. Alright, let's go ahead and look at our second example, which is the opposite of the first example. So in this case, we have to look at a Y network and convert it into a delta. So again, let's go ahead and superimpose it onto a delta network. Now to do that, I'm going to need to redraw this to make it more look like a Y network. So let's do it over here. That, and my delta network is going to look like this on the outer. Looks like a logo. So let's get that. Empty spots for resistors, and my original are gonna look like that. My new ones are gonna look like this. And if you ever forget orientations, you can always just connect the lines and remember what they look like. Again, I could just label these any which way I'd like, as long as I'm consistent and I get the relationship between the resistors correct. It really doesn't matter what I named them. So I have to make sure that I stay consistent no matter what. So this is how I'm going to define them here. It's good practice to just scramble the letters and not rely on memory of letters, but a memory of the relationships that are between each pair of resistors, or each set of resistors. So let's go ahead and begin with RA. So RA is going to be what? It's going to be, and actually before we do that, let's do the same thing as before, and let's make a variable called let's say R bar, and that's going to be the numerator, and that is going to be all the combinations of R1 and R2 and R3 as we saw before. We're going to do that to make our lives easier. 2, 3 plus R 1, 3. So that's going to be this multiplication of each. So one time the 1 and 2 are going to be 15, plus 2 and 3, those are going to be 27, plus 1 and 3, they're going to be 45. Now let's go ahead and sum these up. And we get 87. And the numbers are, they may or may not come out nicely, they're just random numbers. So let's go ahead and we found the numerator. Let's go ahead and find RA. Now if you recall, it's going to be the sum divided by whatever resistor is opposite to our resistor of interest, but in the Y network. So in this case, that's going to be R2. So I'm going to have the sum, which is 87 over the value of R2, which is 3. I'm going to have 87 divided by 3, which is about, or it is 57. Let me actually make sure that's correct, because I didn't have a parentheses. 87 divided by 3 should actually be 29. 29 ohms there. Then I have RB, which I'm going to look at here, and then the opposite resistor there in the Y network is R1. So I'm going to have 87 divided by R1, which is 5. So 87 divided by 5, that's going to be 17.4 ohms. Then I'm going to have RC, and there I have the sum, which is 87 again, divided by what's opposite to it in the Y network, which is R3, and that's 9. So when I divide those out, I get roughly 9.7 ohms. So if I draw the new circuit again, it's going to look like something like the following. Oops. Do this. Draw the RA. And the values are going to be RA is 29 ohms, RB is 17.4, and RC is 9.7 ohms. And do recall that what this is telling us is that if you look at the terminals defined as such, so 1, 2, 3, 4, same thing here. What it's telling us is that these are equivalent between each terminal. And same thing over here. 1, well, 2 and 4 could be the same thing. You just extend them. And 3. So this is the conclusion of this example. Let's move on to the next. Alright, now in this example we're going to see why delta conversions are useful, and we're going to see an actual application of it. So suppose you're given a circuit as such, and you're asked to find the equivalent resistance looking through terminals 1 and 2, as well as the current flowing through the entire circuit, provided that you apply a 120 volt DC signal or DC voltage at the terminals. Now normally you wouldn't be able to do this with the skills that we learned in the previous lectures. So with what we've learned so far, we can do a couple of things. So one, first of all, let's define our goal. What is our goal? In order to find R equivalent, what we need to do is to make the circuit or transform it in such a way that this resistor, this problematic resistor here, 10 ohms, is no longer going to be a problem, and it's not going to be on the way. In some way, we need to break this apart and make it so that get it so that we turn it into a series and parallel resistors, set of resistors. So what we're going to do is we could either we could look at any given set of nodes relating to this 10 ohm resistor and decide what we want to do. So just looking here, I can see that we have a Y network here. As you can see, one branch here, and the other here. That's a Y network or a T network. Similarly, we could have a T network here, from here to there to there, or we could have two star networks, or we could have two delta networks, which is one is this circuit and the other is this circuit. We could use any of these to be able to see how we can simplify our circuit. So what I'm going to target is I'm going to change my my top delta circuit, and what that's going to look like is the following. So we have the equivalent circuit here, and I'm just going to take the voltage source out for now because we're not going to need it until the very end when we simplify the equivalent resistance. So let's remember that our goal is to find the equivalent resistance here. So I'm going to go ahead and take away these question marks and just start labeling my resistors. Let's just call this let's see here, let's call this guy R1, R2, and R3, and pay attention to where things are placed so that we can do it correctly. So you can also superimpose it here to be able to see it easier. What's adjacent to what will help us determine that. So if you're looking for R1, so that's part A. Part A is just to find R12, which are these terminals, the equivalent resistance. Now, what I'm going to do is start looking for R1, and that is going to be whatever the product of 5 and 20 is, because if you can, as you can see here, if I bend this guy this way and bend this guy that way as they attach, these guys will be the adjacent resistors to the R1 resistor there. So that's going to be a 2 times a 5. Now, before I do that, let me just quickly define the sum again. The sum of the R delta, that's going to be 5, 10, 2. That's going to be a 17 ohms. So that's all going to be over 17. So what we end up getting then is roughly 0.588 ohms. Now let's move on to R2. And for R2 then we're going to have, we're going to look at where it's located. It's located here. What is adjacent to it? It's going to be 2 ohms and 10 ohms. 2 times 10 is going to be 20 over 17. It's just going to be twice that, which is, let's find that out. It's going to be 1.176. I'm just going to keep some decimal places to carry over till the end and then round off. So now let's go ahead and find R3, which is this guy. What is adjacent to it? It's 5 and 10, or 5 and 10, which are going to be 50 over 17, which gives us roughly 2.94 ohms. 2.94 ohms. So now you can see here that this has simplified our life in the sense that now that we found some values here, what we can do is go ahead and simplify the circuit down even more. In this case, I've written the values that we just found over near the resistor labels. And the next step, what we can do is combine. Let's see, let me find a nice color. So we can combine these values of these resistors in series, and these resistors in series as well, and also these resistors. Because we've had some practice, I'm going to go ahead and skip some steps and just do these steps simultaneously, so that I get 3 equivalent resistors of the values shown here. So you add these two, you get 52.94. You add these guys, you get 21.176, and you add these two, you get 10.588. Then we take these guys in parallel, and I've already gone in and calculated this, but just take the resistors in parallel, and you get the following. You get 15.126. That makes sense because it should be smaller than either one of them. The smallest one, it should be smaller than the 21. Then you add these guys in series, and you get 25.71. So we found part 1. So for part 1, we found that R12 is roughly equal to, let's just go ahead and approximate it, which was 25.7. Let's just say 25.7 ohms. So let's understand what we did here. We went from a circuit where we didn't know how to find the equivalent resistance of, to a circuit where we to a simplified version where we could do that. Now do keep in mind you could do either one of these delta circuits or two different star networks if you want to do that. But just keep in mind, don't do too much of it. Only do enough to simplify your circuit in such a way that you can just get rid of the problem resistor. So you can break that apart into something simpler and just follow the rules that we learned in previous lectures. Now let's go ahead and find the next step, which is to find the current. Equivalent current flowing through here is going to be just Ohm's law. So this is the same thing as, let's go down here and draw it there. If I have the voltage source going into here, that's what the idea of equivalent resistance is. So I'm going to have to draw that here, and I believe I said that's 120 volts with some current I flowing here. So it's just going to be Ohm's law, which would indicate that I is equal to, let me just write that down here and then summarize it up there, is equal to 120 volts divided by 25.7, and this is just Ohm's law, and it is going to give us roughly 4.67 amps. That is roughly what we get, and that is going to be our final answer there. Next we're going to take a quiz. Alright, so let's look at the quiz problems. For the first problem, we're asked to find RAB in the network below, where A and B are the terminals shown. And of course, we're going to have to use the techniques we've learned in this lecture. And for problem 2, we were asked to find RAB as well for the same terminals. And again, we have to use the techniques we learned in this lecture. My advice to you is to do it in such a way that you get rid of the actual problem that arises. Don't just apply it because you can. Apply it to the place where you think it would solve the issue that you're seeing in the circuit. So that would be my suggestion. Please now pause the video and give these problems a try. Okay, so assuming that you've tried these problems, I'm going to go ahead and solve them. So for the first problem, I'm going to take a look at the circuit, and I'm going to immediately notice that what's given me the problem for not being able to apply the rules for series and parallel circuits is this R1 over here, because it's in a place where I can't combine it with the 5 ohm, the 10 ohm, this other 5 ohm, or the 4 ohm. I can't easily combine it either in series or parallel. So what I'm going to do is I'm going to say, okay, I can choose between a variety of circuits that relate to this 1 ohm resistor. That's the key. We have to make sure that when we're simplifying the circuit, it has to get rid of this problem. That's what we have to focus on. So, because we can see that the rest of them, once this is fixed, or once this resistor is found in a manner where its equivalent replaces it and it makes it more convenient, then we don't see any other major problems here. So what I'm going to do is I can look here and see that we have multiple options. We can either work on this delta circuit, and how I know it's a delta is I'm thinking in my head that, okay, I have a resistor here, here, and here, and not in series, but sort of 3 branches that are connected to each other, and if I sort of bend this guy to down this way and the 10 ohm down this way, it's going to look like this, like that. So I'm thinking it's a delta circuit or delta network. So what I could do is either choose that one or choose the other delta network down here. I could also do a choose either one of these star networks, this one or this one. And I know it's cluttered, I apologize for that, but these are all the different combinations we can use here. What I'll go ahead and do is I'll use the in this case I will go ahead and use the or start with the star configuration with the 1 ohm, 5 ohm, and the 4 ohm. So I'm going to go ahead and redraw the circuit now. Okay, so as you can see, I have redrawn the circuit given the particular conversion that I chose. So I'm going to label that step 1. And I'm going to redraw it here just so we can see it better. So suppose we have the original Y network here. Let me twist it a little bit so that we can impose the delta network on there. So we have the 5, the 4, and the 1 here. And I'm going to use a different color in the delta network, which will look something like this. Now I've labeled these, I should have probably used blue, but I labeled these R1, R3, and R2. And again, it doesn't matter what we label them so long as we stay consistent with the relationship between those pairs of resistors and our original network that we want to convert from. So in this case, as we talked about this before, the way we would do this is we would say, okay, let's find our numerator, and what that's going to be is going to be the all the possible combinations of each pair or I should say it this way, the product of each possible pair of the 3 resistors in the Y network. So it's going to be 1 times 5 plus 1 times 4 plus 5 times 4. So that's the pairwise combinations there. We sum that up, we get 9 plus 20, which is 29 ohms. So we found the numerator. The next step is for any given resistor that we're interested in, we would do this. So we would say, okay, let's find R1. So R1 is opposite to the 1 ohm resistor here inside the Y network. Do remember that we're going to reference the opposite resistor in the original network that we want to convert from, the Y network, not the delta network. So I'm going to say 29 ohms over 1, which gives me 29 ohms. Then I'm going to find R2 by looking at this guy and looking at what's opposite to it in the Y network. That's a 4. So I'm going to have the numerator divided by that particular resistor, the opposites. That gives me roughly 7.25 ohms. And lastly, I'm going to look at R3, which is opposite to the 5 ohms. So I'm going to say 29 divided by 5. And that is 5.8 ohms. So I'm going to fill these out. So instead of having R1, R2, and R3, I'm going to have 29, 7.25, and 5.8. In the next step, I'm only simplifying the network so that it looks like a familiar circuit. So I'm taking the 7.25 and moving these nodes such that it looks like a parallel combination, which it is. Then I'm taking the 5.8 ohms resistor and taking it in parallel with 5. I haven't calculated it yet. That's for the next step. And I'm finally separating the 29 and bringing it this way so it looks more like a parallel resistor with both the 10 ohm and the equivalents of these resistors. Okay, so in the next step, in the third step, we're going to simply combine the parallel resistors shown in let's see, in this particular section of the network, and also in this section. I've gone ahead and shown the results here, or shown the calculations here. You simply take these in parallel, and that gives you about 4.2 for this section, and I've written that here. For the next section, 5.8 and 5, you get roughly 2.68, and that is that. In the fourth section, I've simply added resistors 4.2 ohm and 2.6 ohm in series, and you get 6.88. In the fifth step, I'm going to go ahead and denote that here. That is the fifth step. And what I'm going to do here is take the 6.88 and the 229 ohm resistors in parallel, and that's going to be a 6.88 and a 29 over 6.88 plus 29, which should roughly give us which gives me about 5.56 ohms, and that goes here. Now in the sixth step, we go ahead and do the final step, which is to combine these guys in parallel, and that's going to be a 10 times a 5.56 over a 10 plus a 5.56, which should be roughly 3.57 ohms. So in other words, R equivalent, or RAB, is roughly 3.57 ohms for the circuit shown. Let's go ahead and box that, and let's now go ahead and simulate the circuit only in fault stat circuit simulator. That's just because we're still working with passive resistive networks, and we don't enter DC, and we don't necessarily have to go to LT Spice, but later on we definitely will. So let's go ahead and see what this model looks like. Okay, so let's go ahead and start the simulation. And as you can see, for a 1 volt DC signal applied to the terminals of the equivalent resistor as well as the original network, you can see that for 1 volt we have 280 milliamps, and similarly for the equivalent one we see a 280 milliamps current for the 1 volt. So that verifies that our circuit is indeed, our operations have been performed correctly, and the theorems hold, and that summarizes this problem. Okay, so for this problem we also have multiple options for simplifying our issue, which is this 10 ohm resistor, because if it wasn't there we could simply combine the 15 and the 8 in series. We could then take it with parallel with 5, and then combine that with the 20 in series, and then finally add it again with the 5 ohm in series, and that would have been done. But because it is 10 ohm resistor, we have to somehow relate the 3 resistor combinations with this 10 ohm. So the only one we can do right now is the one involving all 3 of these resistors. So let's go ahead and draw the equivalent circuits. Okay, so I've gone ahead and drawn the equivalent circuit by first thinking in my head. I'm rearranging the circuits here as such. The delta network is going to be rearranged in this way so that we can see it easier. And what I'm going to turn it into is the following. I'm going to think of the 3 resistors as such, and I'm going to place it exactly where the terminals are that they're being used in. So in terminals, let's call them 1, 2, and 3. Those are these terminals, which then translate to oops, that's not the right terminal. It would be down here, that would be called 2, and that would be 3. So I'm simply placing it there, and I will be finding R, let's just call it R1, R2, and R3, and let's label these because they didn't change. So in step 1 we only simplified the schematic, simplified the network. In step 2 we are going to find R1, R2, and R3. So for R1 we're going to find the rules we learned for delta to Y or delta to star conversions, which is to say, okay, let's say I want to find R1. What I would do is first I will find a summation of all of the delta resistors. So this would be sum R delta, which would equal 10 plus 20 plus 8, which is equal to 38 ohms. And what I would then do is say, okay, if I want to find R1, what I would do is take the product of the adjacent resistors in the delta network. Let's remember our designations and the rules. So 10 times 20 is these are adjacent to R1 divided by 38. So that would be 200 divided by 38, which would give us roughly 5.26 ohms. Then we have R2, which the adjacent resistors are 20 times 8. That's divided by 38. I could go ahead and simplify that, but I'll just go ahead and plug that in for now. That is not the salient point here. The concept is demonstrated, and the answer is going to be roughly 4.21 ohms. And then for R3, then we're gonna have R3 has 10 and 8 adjacent to it, so 10 times 8 over 38, which is roughly, what was it, 80 over 38, which gives us about 2.1 ohms. So let's clear these and write the answer for them. And I believe that R1, 2, 3 was like that, so R1 is going to be 5.26, R2 was 4.21, and R3 was 2.1. Now in the next step, actually what I'm doing here is I'm simplifying, so let's do that first. Let's see, what did I do here? Okay, so for the first step I did the conversion. So I didn't simplify here, I apologize for that. What I did there was I converted the circuit, so I convert to star or Y network, go from a delta to a Y. And for the second step, I found the values, and for the how do I want to say this? So let's see. Just to be consistent, let me take 2 out of here. So I simplified the network, or converted to Y, and then found the values of R1, R2, and R3. And for step 2 then, what I did was to simplify it in such a way that it's, so here I simplify the network, and write the values here, 5.26, 4.21, and 2.1. For the third step, we're going to sort of do a couple things at the same time, because it's easy now that we've learned some of these skills. So what I've done is I've simply combined 3 different steps into one, which is the addition of all these individual resistors in series. Okay, so I've gone ahead and done these steps. So I simply added these resistors, and these pair of resistors, and the answers are shown here as well as on the schematic itself. And for let's see, I'm getting the steps sort of okay, so that would be 3. Okay, so for the fourth step, what I'm doing here is I am simplifying one step further by combining these two resistors in parallel. So I have 9.21 in parallel with 17.21 over the sum, which is going to give us about 6 ohms. So I'm going to write 6 ohms here. Then I have a 10.26 there. And finally, for the last step, which is step 5, I'm going to have to just add up these two, which gives me so 10.26 plus 6 is going to give me 16.26 ohms. And that is my final answer. Let's go ahead and write that. RAB is roughly equal to 16.26. We box that, and now let's go ahead and simulate this in fault stat circuits. Okay, so here are two circuits that are supposed to be equivalent. Let's run the simulation, and we see that for a given 1 volt DC input, we get the same 62 milliamps flowing from the source and going into the circuit, and that tells us that the resistance looking into nodes A and B are the same. This concludes this lecture, and I will see you guys in the next lecture discussing the methods of analysis.